Hello, let's talk about physics. This is video lecture 8.3, part 2. And in this lecture, I am going to summarize the key ideas in the last two sections of chapter 8. Those are sections 4 and 5. Chapter 8, section 4 is about the work done on a system by an external force. What happens in such a case to the energy of a system like that? And section 5 is to step back and look at the whole concept of conservation of energy again from a slightly broader perspective, as we'll see. Okay, so here are the key ideas you need to know. First, something I've said before, but it bears repeating. Work as a physics concept represents, at its most fundamental level, energy transfer between a system and its environment or surroundings. A little more specifically, work is energy transfer by means of a force between a system and its surroundings. Next semester, we'll learn about other ways to transfer energy between a system and its surroundings other than a force. But for now, that's what we're looking at. Work is energy transfer between a system and its surroundings by means of a force. And in the very, very big sense, we have a statement that really, I think, makes very fundamental sense. The total energy E of a system can change, but only by amounts of energy that are transferred to or from the system. The only way you can get the total energy E of a system to change is to dump some energy in or to take some energy out. And if you have a system which at some point in time has a total energy of 100 joules, and then you, perhaps by means of work, transfer in 10 joules of energy, you will find that the total energy of your system has gone up by 10 joules to a grand total of 110 joules. Conversely, if you started out with 100 joules of energy total in your system, and the work extracted 10 joules of energy, then you'd find the system was left with only 90 joules. In other words, if you had 100 joules of energy and you discovered that 10 joules of work were added, but nothing else happened, you wouldn't discover the total energy was 108 joules, or 109, or 111. If 10 joules went in and you had 100 joules to begin with, you'll have 110 joules. It's that simple. Now, the next pictures here are very schematic representations of this idea. Somehow we have chosen a system, and this dashed curve shaded blue inside is just a generic way to represent some system we have chosen. And the picture on the left represents positive work being done on the system by some force. Then, if it's positive work that's done on the system, the direction of energy transfer is into the system. That arrow is the direction of energy transfer. And if positive work is done on a system by external forces, then energy is being transferred into the system. Conversely, if negative work is done on the system by external forces, the direction of energy transfer is out of the system. Those are the only two possibilities with work. If you have positive work done by external forces, energy is going into the system. And if you have negative work done by external forces, energy is coming out. All right, now let's just take a little bit of time and expound on those ideas a bit. Let's start by avoiding the complication of friction. So let's consider a situation where there's no friction involved. What I'm going to describe to you is just a simple little game called bowling ball hurling or throwing. In this game, the participant stands at rest on the ground holding a bowling ball. And the person is probably squatting down close to the ground with the bowling ball at rest. And then they are going to use their body and arms to stand and push up on the bowling ball and let go and hurl the bowling ball into the air. The winner is the one who can get the bowling ball to go the highest, but I'm not interested in that. I'm interested in what happens while you are exerting a force on the bowling ball and lifting it up. I'm going to talk about work and energy ideas in that process. Okay? All right. Now, for the bowling ball, let's think about the forces that act on it and do work. There's you. Your hands are pushing on the bowling ball, and the bowling ball is being displaced upwards, so there's definitely work done by you. But also, because it's going upwards, there's work done by the gravitational force. So we're going to take for our system to be our particle, that's the bowling ball, and because F-grav does work, Earth. If F-grav does work on a particle, always include Earth, because F-grav's a good force, it's conservative. So we're going to take our system to consist of the ball plus the Earth. That's what we're going to choose. If that's what we choose, notice, then our pushing force from our hands is external, because we didn't include us, for a very simple reason. Our force isn't conservative. Generally speaking, don't include non-conservative forces in the system. There'll be one exception coming up, but generally speaking. Okay, so since we didn't include us in the system, the player, our force from our hands is an external force, and it's definitely doing work on the bowling ball as I'm lifting the bowling ball up. And it's doing positive work because my force is up and the displacement is up. So what I have here in this case is external positive work done by me, and that's sending energy into this system. Again, the system is the bowling ball. There's that. And you can see they've included the ground to represent Earth. Okay? All right, now, if we have energy coming in by means of external work, the only thing that can happen is the total energy of the system goes up by the same amount as the energy coming in from the work. Now, what's going to happen to the total energy of this system? Well, I contend that it's going to change, it's going to increase, and it's all going to be change in mechanical energy of the system. Why? There'll be a change, an increase in kinetic energy, delta K, greater than 0, an increase, because the bowling ball speeds up. Initially it's at rest. When I let go, it's not at rest. So the kinetic energy is increased. Delta K is greater than 0. Also, there'll be a change in gravitational potential energy, and that will also be greater than 0 because the ball is higher than it was to begin with. So there'll be a change in mechanical energy that will be greater than 0. There'll be an increase in the mechanical energy. And there will be an exact increase in the mechanical energy equal to the amount of work I did with my external force. And that's the energy statement right there. The external work I did with the pushing force from my hands, however much that is, in Newton times meter or joules, is exactly how much the mechanical energy of the system will go up by. Okay? If I do 20 joules of work, W external, then the mechanical energy will go up by 20 joules. And that 20 joules will be divided up between delta K and delta U. And without saying more information, I can't tell you how. It might be 10 joules and 10 joules. It might be 12 joules and 8 joules. But the change in the mechanical energy will be 20 joules if I did 20 joules of work. That's the idea here. If you have external work done, then that's how much the total energy of the system will change by. And we didn't have to worry about friction here. Now, what if we have friction? That does add a little bit of a complication, but we need to be able to deal with it. Because let's face it, it's pretty common in everyday situations where objects with rough surfaces are sliding across each other, and we have to be able to deal with that. So now I want to look at a situation where there's a frictional force involved. Specifically, kinetic friction will be important here. I need the surfaces to be sliding across each other. Let's take a simple situation like we're pretty used to. a horizontal floor with an x-axis. My particle is a block. The block has some initial velocity to the right, and therefore some initial kinetic energy. And I'm going to pull it with an applied force. That's coming from me, right there, to the right. And as a result, after a displacement d of some amount, it'll have a final velocity bigger than the initial velocity. So it'll have a final kinetic energy bigger than the initial kinetic energy. So the change in the kinetic energy of the block will be greater than 0. It's a horizontal surface, so there's no change in y coordinate of the block. So there's no change in u gravitational. And there's no spring at all here, so there's no u elastic whatsoever. But the surfaces are rough. The bottom of the block is rough, and the floor is rough. So as the block slides to the right, I have a kinetic frictional force acting on the block to the left. The block slides a distance d, notice. All right, let's pick a system and apply a work energy idea to it. Okay, clearly I want to include the block. That's the key particle. Note that there is a gravitational force on the block, of course vertically down, but the block is displaced horizontally. So how much work does the gravitational force on the block do here? Did you say 0? Because the gravitational force and the displacement are exactly perpendicular. Okay? So there's no work done by the gravitational force, which is consistent with the fact that delta U grav equals 0. So you don't need to include Earth in the system. You can if you want, but it's a non-player here because it doesn't do any, F grav doesn't do any work. But here's the key thing because of the kinetic frictional force. What happens energy-wise when rough surfaces slide against each other? You can demonstrate that for yourself. Rub your hands together vigorously. Right? Those are rough surfaces sliding against each other. You can feel what's happening, right? Don't your hands feel warmer? Do it if you haven't done it. Do it. Come on. Your hands feel warmer. That's because you're making the atoms and molecules in the surfaces, your hands, jiggle faster. And that jiggling of atoms at the microscopic level is called thermal energy. We'll learn more about that next semester too. But the bottom line is, when rough surfaces slide against each other, thermal energy is created. And since I have rough surfaces here with a kinetic frictional force over a distance d, there's going to be an increase in thermal energy, but it's going to be shared between the block and the floor. So, bottom line is, I have to include the floor as well in the system. And that's what this dashed line is conveying. It surrounds the system. There's the block, and that part of the floor that is the distance d, over which the block slid. That's my chosen system. Did not include me, because my force isn't conservative. All right, so now let's apply the work energy idea to this system. All right, because I'm pulling to the right with my applied force and the displacement's to the right, I'm doing positive work. So there's work done by an external force, me, that represents energy transferred into the system. And however much work I do in joules, that's going to show up as a total energy increase of the system. And that total energy increase is going to show up in a couple of ways. Because the kinetic energy increased, you could say that the mechanical energy increased. Delta E mechanical is greater than 0, right? Because mechanical energy is kinetic plus potential. So if the kinetic energy goes up, the mechanical energy goes up. So part of my work and energy transfer in goes into increasing the mechanical energy. But also part of it goes into increasing the thermal energy of the surfaces, the bottom of the block and the floor over the distance d. All right, and please note, thermal energy can only, when surfaces rub against each other, increase. When you rub rough surfaces against each other, they never get colder. And so when rough surfaces rub against each other, we have an increase in thermal energy. So delta E thermal here will always be positive. So I have mechanical energy that has increased. Delta E mechanical is greater than 0. And I have thermal energy that has increased. Delta E thermal is greater than 0. Where did those energies come from? My external work. And however much external work I did, that's how much I have to contribute to the two forms of energy on the right side. In other words, if I do 20 joules of work with my external force, then I have 20 joules to distribute between E mechanical and E thermal. And I will need more information to figure out exactly how that happens. It might be 10 joules here and 10 joules here, or it might be 12 joules here and 8 joules here. All right? You would need more information, but you know the total has to be 20 joules. And the idea is really that simple. If you would have a certain amount of energy transferred in, then the total energy has to go up by that amount. Conversely, if there's a certain amount of energy transferred out of a system, then the total energy of the system has to go down by that amount. Think about a banking situation. Let's say you have a savings account in a bank. If you transfer in $50 into your savings account at an ATM, then you expect your balance to go up by $50, not 40, nor 60, even though that might be nice. If you transfer in $50, then the balance has to go up by $50. It's that same idea, just applied to a physics situation, not an economical one. All right, with that we are ready to state our most general energy principle to date. We'll make it even more general next semester, but for now, here it is. This is what I just call our general energy principle, of which conservation of mechanical energy is just a special case. Okay, here's what it says. Any energy transferred into or out of a system must come from external work. So that's going to be the left-hand side of this principle. External work represents an energy transfer into or out of a system. That's going to be on the left side of our equality here in our energy principle. But however much energy is transferred in or out by external forces, however much that is, on the left, that's how much the total energy must change. So on the right, I have various changes in various forms of energy. Because energy comes in many different forms, and the total that we dump in can get distributed amongst these various forms, which makes it a little bit complicated. But the three forms to consider that we will have of energy changes in the system are the mechanical energy can change, delta E mechanical, and that itself can show up in a change in kinetic energy, a change in gravitational potential energy, and a change in elastic potential energy. A change in thermal energy. That's going to be the case whenever rough surfaces slide across each other. And you need to include the surfaces in your system. By the way, there's a simple formula for calculating how much the thermal energy increases when rough surfaces slide against each other. And the formula I'm just stating for you is right here. It's very simple. Take the magnitude of the kinetic frictional force acting on either surface multiplied by the distance of sliding, d. Okay, that's the sliding distance. So that can also take part of the external work energy that came in, delta E thermal. And if you have rough surfaces sliding against each other, then you will have delta E thermal. Another thing that can happen in principle is there can be changes in what are called internal forms of energy that aren't thermal. Thermal energy is from atoms jiggling, which is a kind of internal energy, and the delta E internal is any other internal energy change other than atoms jiggling. Bottom line is, I'll say right now, for most of the cases we're going to consider this semester, do not worry about delta E internal. So pretty much don't worry about it for this semester. Okay? So then what's really the important part of this general energy principle is that external work will equal whatever change in mechanical energy is present plus whatever change in thermal energy is present. Now let me look at just a couple of special cases of this general energy principle. Since it's general, it ought to apply pretty much whenever we need it. What if we have what's called an isolated system? An isolated system means by definition that there are no external forces doing work. None. No external forces doing work. i.e. W external is 0. That means the left-hand side of the energy principle is a 0. So let me write it. Right there it is. There's a 0 on the left. There is no energy coming in or going out to or from the system. If that's true, then if there are mechanical and energy changes and thermal energy changes, their total must equal 0. And you can have a situation like this. We'll come across it. But now note something. If I've got a delta E thermal because I have rough surfaces sliding against each other, please remember, delta E thermal is always greater than 0. Remember, when you rub your hands together, they never get colder. Delta E thermal will always be greater than 0. That's going to require, since delta E mechanical plus delta E thermal equals 0 in this case, that delta E mechanical is less than 0. So the thermal energy is going to go up, but the mechanical energy is going to go down by exactly the same amount. And that's all that can happen with an isolated system with rough surfaces sliding against each other. You might create 2 joules of thermal energy, but you will have lost 2 joules of mechanical energy. All right, let's do one more kind of special case. What if I have an isolated system? That means no external work and no rough surfaces sliding. None. Then W external equals 0 and delta E thermal equals 0. If all the surfaces are smooth, frictionless, then when they slide across each other, they don't generate any thermal energy. So W external equals 0 and delta E thermal equals 0. So that means there's a 0 in our energy principle. There's a 0 for the W on the left, and there's a 0 for the delta E thermal. So the only thing left is delta E mechanical, but that must equal then 0. The mechanical energy can't change. Well, that's exactly what we called conservation of mechanical energy. No external forces doing work, and of the internal forces doing work, they must all be conservative, gravity and spring. That means there can't be any rough surfaces, because if there's F kinetic, that's not a conservative force. So the whole thing about conservation of mechanical energy, which we did in Chapter 8, Section 2, is just a special case of this general energy principle. Okay, we're going to be doing some more practice with this in our class sessions. But let me do one here with you now, and then leave a class engagement exercise for you to do. Okay, so here I want to do a little bit of practice applying our general energy principle. Okay? All right, here's the scenario. In figure A, it's on the left, you pull upward on a rope. Right there. You pull upward on a rope that is attached to a cylinder on a vertical rod. Because the cylinder fits tightly on the rod, the cylinder slides with considerable friction. It's not smooth. Okay? We're going to tell you that your applied force does positive work in the amount of 100 joules. And we're going to take for our system, this is really important, to be the cylinder plus the rod plus Earth. In fact, picture B is a schematic representation of our system. It's got dashed lines surrounding the cylinder and the rod and Earth. We picked Earth because F-grav does work. But we didn't include us, because our force isn't conservative from our hand. And so we're doing work, 100 joules, but that represents external work then, doesn't it? That's this. And it's positive, isn't it? So that means there's energy being transferred into the system from our work. Now, part C of this diagram is a very generic, or very abstract picture that is what we call an energy statement for the system. It's showing all the energy changes within the system and the energy transfers into or out of the system by means of work. Okay? So it just draws a box, and inside the box we represent changes in system energies. And then there's this arrow that represents our external work and energy going in by an amount, 100 joules. Now we're going to tell you a little more information. As a result of what's going on, the kinetic energy of the cylinder increases by 50 joules. That means the kinetic energy of the system increases by 50 joules. And the gravitational potential energy, U grav, increases by 20 joules. That means delta U grav is positive 20 joules because it ends up higher. The only other change in energy within the system is thermal energy, because as the cylinder slides along the rod, there's friction. So there's going to be an increase in thermal energy. Yes, increase. Our task here is to find the change in thermal energy, delta E thermal. All right, this problem set chose for us a system. So all we have to do is apply our general energy principle to this system. The general energy principle says any external work must show up as a change in the total energy of the system, and that change in the total energy can show up in several forms. Change in mechanical energy plus change in thermal energy, and we won't worry about any changes in internal energy. We would have to tell you if that was happening. Now, for change in mechanical energy, in general, there are two forms. Well, there's multiple forms. There can be a change in the kinetic energy as part of delta E mech, and there can be a change in the gravitational potential energy, delta U grav, as part of delta E mech. And then there's still delta E thermal. Okay, so all I did was represent delta E mechanical as delta E kinetic plus delta U grav. No springs here to worry about. Okay, let's think about what we know. I know how much work I do. That's external work, 100 joules. I know how much the kinetic energy changes. It's an increase of 50 joules. I know how much the gravitational potential energy changes. It's an increase of 20 joules. So I think I can just solve this energy principle for delta E thermal, right? Just solve algebraically. But do the algebra correctly. Delta E thermal equals external work minus change in kinetic energy minus change in U grav. And then plug in the values on the right-hand side with appropriate signs. Your work, your external work, is positive 100 joules. Make sure this is visible here. Okay? Minus the kinetic energy change, positive 50 joules, right? Minus the gravitational potential energy change, positive 20 joules. And 100 minus 50 is 50, minus 20 leaves me with positive 30 joules. And the positive is very reassuring because thermal energy changes when rough surfaces slide against each other must always be positive. And that's how much? 30 joules of thermal energy is created in this situation. Okay? Now there's not any hard math, we're just applying the energy principle to get some practice. So now here's the one I want you to do for class engagement. So I want you to give me your answer on Blackboard. Okay? All right, so this is going to be for class engagement. On Blackboard. Heads up on this one, a little different. Normally on Blackboard with these class engagement exercises, I just have you type a couple of word answers. Here, I'm going to want you to draw a picture and do some work on a piece of paper, snap a picture of it, save it as a PDF, and upload it to Blackboard. Just a little bit more here because we need to do some drawing. Let me explain what's going on. We're going to just take the example I just did and add just a little more to it. Okay? So the arrangement shown below is similar to the one I just showed you. Cylinder and a rod. Okay? And now this time you pull with your applied force downward on the rope that is attached to the cylinder, and the cylinder fits tightly on the rod. And the cylinder will descend, it will go downward, but as it does, the cylinder pulls on a block by means of a second rope, and the block slides over a lab table. You can see there what's going on. Again, we take the system to be cylinder plus rod plus earth, just like we did in the previous example. And here comes some information that's going to be important. Your work on the system is positive 200 joules. You do positive work because your force is down and the cylinder's displacement is down. So that's positive. Positive work done by you. Okay? But the system does 60 joules of work on that block. Now, within the system, the kinetic energy increases by 130 joules, so it speeds up the system, and the gravitational potential energy decreases by 20 joules because the system goes down. Two things you need to do in this exercise. You need to draw an energy statement for the system, like was drawn in figure C in the example above. That's where you're going to need a piece of paper because you need to draw the energy statement. The energy statement is the appropriate version of this kind of picture right here, but now applied to this new situation. Okay? So you need to draw and carefully label all the parts of the energy statement for this system now, right there. And then, showing your work, you need to find the change in the thermal energy of the system. So do this, please, on a piece of paper. Take a picture, save it as a PDF, and upload it to Blackboard. And that's our class engagement. Okay? Okay, now there's going to be another video where I do an example problem using the general energy principle, but that's all for this video.